Okay, another way of saying that, 6.022 times 10 to the 23 carbon atoms have a total mass of 12.01 grams. Okay, that's just translating into a sentence. Okay, molar mass of oxygen is 15.999 grams per mole. What that means is a mole of oxygen atoms has a total mass of this. Okay, what's the mass of 1 mole of titanium atoms? 47 point something? 867? Yeah. Okay, and the way we would write that in terms of the unit is grams per mole. This many grams per mole of atoms that I have. Okay, so the unit that we're going to be using for molar mass is grams per mole. Okay, it's a ratio. And this amount is going to be different depending on the element. If I have a mole of carbon atoms, they weigh about 12 grams. If I have the same number of oxygen atoms, it's a little more. Why would the same number of oxygen atoms have a bigger mass? It's the same number of atoms. Why would the oxygen be heavier? Exactly. Each individual oxygen is a little heavier. So even though I have the same number of them, the mass is going to be different. Titanium is way heavier than both of these. So even though I have 1 mole of them, they individually weigh more. I don't like saying weigh with mass, but it's okay. It's going to be a bigger number because the individual items are larger. Okay? Kind of makes sense? Okay, stop me if you have questions. Okay, molar mass of an element is equal to the mass of a single atom of that element, but with that unit of grams. Okay, I'm just kind of I already said this. Okay? So we talked earlier with the candy. If I know the total mass and I know something about the individual item, I can count the number of items. Okay? The chemistry version of what we've been talking about is if I know the total mass, which is very easy to figure out because you just weigh it on a scale, right? Just dump your sample on the scale, you get the total mass. And I know the molar mass, aka the mass of the individual elements I'm dealing with, I can then translate that or convert it. Yes, we will be doing picket fences. We're going to convert into the number of items. Okay? And when I say number of items, we're counting them in groups of moles. How many moles do I have? Do I have 1 mole, 2 moles, half a mole? Well, we can figure it out based on mass. We can now translate mass to number of items. Okay? So the molar mass of silver would be 107.87 grams per mole. Okay, if I had 87.62 grams of strontium, I look on the periodic table, I see that's what that mass is, I have 1 mole. Okay, so we would say that these are the molar masses of those elements. Kind of make sense? I'm kind of saying the same thing over and over again in different ways, but I'm just trying to let it sink in. Okay, let's watch a quick video, and then we'll be almost done.
We got a worksheet today, Mr. Floyd?
Yes, but it's one-sided. There you go.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your ant's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container, or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water.
A mole of water is, if you fill this up to the 18 mark, so just that much water. So just in that little amount of water, you have a mole of water molecules, just in that little amount. So helps you appreciate how tiny molecules and atoms really are.
Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank.
$1 million how often?
A second.
A second. And that wasn't a mole of dollars, that was a mole of pennies. You spend $1 million every second for 100 years and you don't even spend like 1% of your money. It's a lot.
Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream